Imagine pulling up a map on your smartphone. You type in a destination, the screen shifts, and suddenly you've got this perfectly clear, optimized route right in front of you. It feels like an exact objective mirror of the real world, right? Well, here's a little secret. For that map to actually be useful to you, it has to deliberately omit, distort, and alter reality. It acts almost like a digital diagnostic system, aggressively filtering out the noisy chaos of the physical world so you can actually process what's on your screen. Welcome to The Explainer. Today, we're uncovering the hidden algorithmic mechanics behind the maps we rely on every single day. Which brings us to a pretty provocative question. To tell the truth, do maps have to lie? The map on your device is absolutely not a one-to-one replica of the physical world. I mean, if it were, it would just be this chaotic, overlapping mess of microscopic data points. You wouldn't be able to read a thing. Instead, it's a highly edited, constructed reality. Your map literally lies to you about the exact size of roads, the number of buildings, and the shape of coastlines. And it does all of this just so it can tell you the absolute truth about how to get from point A to point B. Okay, let's dive into this. The technical term for this whole hacking process is cartographic generalization, and it's defined as the deliberate reduction, alteration, or emphasis of cartographic information to improve usability. So it's not just taking a massive image and shrinking it down to fit on your screen. No, it's an active, highly mathematical, and algorithmic manipulation of data. Honestly, it's the core competency, the ultimate unique selling point of cartography itself. To understand how this system actually works, let's quickly run through our diagnostic agenda for today. We'll start with the art of map abstraction, the 3 stages of generalization, and the workflow. Then we'll get into the 7 core map operations, peek under the hood at the Douglas-Pucker algorithm, and finally, look at automating the map matrix.
Section 1. The art of map abstraction. Why we filter the noise.
So the crucial point here is that without generalization, both our phone processors and our human brains would simply choke. First off, we have to ensure legibility. Think about it. If a building is 5 meters wide in reality, drawing it perfectly to scale on a 1 to 50,000 map would make it practically invisible. It'd be just a tenth of a millimeter wide. Generalization also lets platforms like OpenStreetMap seamlessly transform massive datasets across 20 different zoom levels without crashing your app. It shrinks data volume so maps load instantly over a cellular network. And most importantly, it adapts the world to your specific purpose. If you're bombing down the highway at 70 miles an hour, you definitely don't need your screen cluttered with every nearby hiking trail. Section 2, 3 stages of generalization, the when and how. And this brilliantly illustrates the entire workflow. Think of this process like film editing, going from shooting raw footage to the director's cut, and finally to the visual effects on your screen. We start out in the physical environment. Through what's called primary modeling, we capture raw data into a digital landscape model. Next, secondary modeling processes that into a digital cartographical model. That's the actual visual map design. And finally, tertiary modeling is what happens entirely inside your head. You look at the map and form a cognitive map in your working memory. At every single step of this chain, data is deliberately lost and abstracted. Because of that, you can never perfectly reverse engineer the real world from the final map you see. Now, looking at those early stages, we actually have 2 very distinct types of generalization. Acquisition generalization happens right out in the field. So when a surveyor is measuring a vast forest, they aren't logging every single pine needle. They might just record coarse vegetation classes. They are actively filtering reality right at the point of measurement. Model generalization, on the other hand, happens later, deep in the database. This is where we take the highly detailed data we've already stored and derive a coarser, simpler digital model from it, like an algorithm combining a bunch of individual residential plots into one solid block. Section 3. The generalization workflow. System diagnostics. The actual procedure breaks down into a clean 5-step workflow. First up, specify the objectives. Are we making a weather map or a subway map? Second, analyze the given data for conflicts. This is huge. If you've got overlapping subway lines in a dense downtown area, that's a geometric conflict. Or if colored zones become too small to distinguish, that's a thematic conflict. Third, you execute basic operations to resolve those exact conflicts. Fourth, you sequence those operations into automated workflows. And fifth, you evaluate the results. Does the map actually work? Section 4, 7 core map operations, the toolkit. Now, what's really interesting about this slide is how simplification completely tackles geometric complexity. Take a jagged black line. That could be a winding river or a complex mountain road. By intelligently deleting intermediate points or smoothing the line, the algorithm morphs complex, messy data into super clean, readable user interface lines. And it does this while magically preserving the essential shape of the original object. The second operation is deletion. And yeah, it's exactly what it sounds like. Sometimes to make a map genuinely useful, we just have to delete entire geo-objects. If a map is bogged down with tiny, irrelevant sheds or minor local roads that don't help the user at all, an algorithm just wipes them out, gone. This creates crucial breathing room and aesthetic clarity, so you can actually spot the major landmarks. Next up in this dynamic toolkit, we have enlargement, emphasis, and displacement. Enlargement forces an object to be drawn way bigger than it is in reality, so your eye can actually perceive it on screen. Emphasis takes that a step further, using striking colors or thick double lines to practically scream, "Hey, look at this major highway." And displacement, well, that's the real magic trick. When you pinch to zoom out and a river and a road suddenly look like they're crashing into each other, the algorithm literally shifts them apart. It falsifies their true coordinates just to maintain a readable relative distance for your eyes.
Rounding out our toolkit are aggregation and degradation. Aggregation merges multiple smaller objects, say a dozen small individual houses, into a single larger polygon that represents a city block. Degradation is essentially the opposite. It steps down in dimension, which is known as a collapse. Imagine a massive, sprawling hospital campus mapped out as a giant polygon. When you zoom way out on your screen, the algorithm collapses that entire massive polygon into a single, simple, recognizable point symbol of a cross.
Section 5, the Douglas-Pucker algorithm. Math in motion. Let's move to a specific example and see how this builds. To simplify a wildly complex curve like a jagged coastline, the computer doesn't actually need a human to draw it. It draws a perfectly straight line from the start point to the end point. Then it searches for the intermediate point that pushes the furthest away from that straight line. If that point pushes out further than a set mathematical threshold, the algorithm decides, okay, this curve is significant, we must keep it. It splits the line right there and repeats the process over and over in a recursive loop. It's automated math instantly deciding which curves of reality actually matter. Section 6, automating the map matrix, the next frontier. Historically, authoritative mapping agencies relied on completely manual rules and incredibly strict printed drawing regulations. If a human cartographer saw a visual conflict, they fixed it by hand based on intuition and a massive rulebook. But today, with digital screens where you're constantly pinching, panning, and zooming, we require dynamic, on-the-fly rendering. So the whole industry is shifting fast from manual human rules toward advanced artificial intelligence and deep learning networks. But as you can imagine, teaching a machine to intuitively think like a master mapmaker is incredibly tough. First, AI needs vast amounts of data to learn, but cartography seriously lacks large, diverse training datasets. That forces engineers to generate super expensive simulated data. Second, how do you even mathematically define a good map to program an AI's loss function? It's highly subjective. And finally, when the AI automatically changes a building's shape, how does it weigh competing properties? Should it prioritize keeping the building perfectly square or prioritize maintaining its exact square footage? Honestly, there are no universally right answers here. The source material perfectly sums up this struggle with current generalization tech. It notes, the solutions presented are often very application-specific and difficult to transfer. This results in a lack of objectivity and transferability. So basically, despite all our processing power, creating a universally perfect, totally objective mapping AI, it remains one of the great unsolved puzzles in modern geographic data science. Which leaves us with a pretty fascinating thought to take away from this explainer. Generalization proves that every single map is a curated story, carefully hacked and filtered so our brains can actually understand it. But as we hand the reins over to deep learning networks and algorithms to make these trillions of micro-decisions for us every second, if an AI eventually draws all our maps, whose version of reality are we actually navigating? Just a little something to chew on the next time you open an app to find your way home. Thanks for joining me today, and keep questioning the world around you.